Hello everybody, today we'll be going over the CSAcademy problem BFS-DFS. We're given the order nodes are visited in by BFS and DFS, and we need to reconstruct the list of edges based on this information. The problem first explains what BFS and DFS are. As a quick reminder, BFS visits the closest nodes first, and DFS visits as far as it can before backtracking. For input, we have n, the number of nodes, a permutation of n nodes, which is the BFS order, and a permutation of n nodes, which is the DFS order. For output, we want to output -1 if there's no valid list of edges, otherwise we output the number of edges and a list of all of them. Let's take a look at our sample case. Based on the output, the graph is built as follows. There is an edge between nodes 1 and 3, 1 and 5, 1 and 6, 2 and 5, 2 and 6, 3 and 4, 3 and 5, and 5 and 6. To confirm this, we can show the BFS starts at node 1, then goes to 3, 5, and 6, and then finally goes to 4 and 2, aligning with the input order. For DFS, we start at 1, go down to 3, go down to 4, backtrack to 3 and go to 5, go to 2, backtrack to 5 and go to 6, confirming that the edge list is accurate for DFS as well. Let's take a look at some observations we can make. First, we start at node 1, and a valid set of edges is not guaranteed to exist. This problem is really testing your ability to understand how nodes are processed in each traversal. For BFS, the closest nodes are visited first. If node V appears after node U in BFS, V must be later than U if it is in the same layer. Otherwise, V must be on a further layer than U. For DFS, paths are fully visited before moving on to new ones. If node V appears after node U in DFS, V must be later than U if it is on the same path. Otherwise, V must be on a different path than U. Now there is a critical detail the problem intentionally omits to avoid making it too simple. Any valid set of edges works. Thus, we really only need to pay attention to these two details. For BFS, we care about appearing later in the same layer. For DFS, we care about appearing later in the same path. Let's take a look at the BFS property first. Node 1 appears first, and then after is node 3, so we can just draw an edge. After is node 5, so we'll just draw another edge from node 1 to node 5. We can continue this pattern for the rest of the nodes, drawing an edge from node 1 to the other node. We can see that doing this, we have every node on the same level, just appearing one after the other. This also does satisfy the BFS ordering as we start at 1, then go to 3, then 5, then 6, then 4, then 2. Now let's take a look at the DFS property. We start at node 1, and then after is node 3. 4 follows 3, 5 follows 4, 2 follows 5, and 6 follows 2. We can see that all the nodes are on the same path, just appearing one after the other. And we can also confirm this satisfies the DFS as the nodes are visited in the order of 1, 3, 4, 5, 2, and 6. Let's look at how this works together now. BFS starts at 1, then visits 3, 5, 6, 4, and 2. Now let's look at the DFS, which starts at 1 again, and then visits 3. After is 4, 5, 2, and 6. Note that the second node must be equal in both traversals. For DFS and BFS, this is the first child. The root node cannot have two different first children, as regardless of the traversal technique, this node will be processed first, so if it is different, this set of traversals is invalid. Let's take a look at the implementation for this problem. We read in n the BFS and the DFS. We then check if the second node, or the first child, is equal. If not, we output -1. Otherwise, we can move on to the BFS. For BFS, we just add an edge from node 1 to each other node. Next, we have the DFS. For DFS, we add an edge between each adjacent pair of nodes. Note that we must not add an edge for node 1 and the first child in DFS as the BFS already handled it. Finally, we output the number of edges, which is 2 times n minus 3, and the edge list. We have 2 times n minus 3 edges, as each traversal has n minus 1 edges, and then we have the extra -1 for the duplicate. This approach has a time complexity of O of n for input and processing the traversals. This approach has a memory complexity of O of n to store the traversal information. That's all for the general explanation of this problem. Now let's take a look at language-specific solutions for C++, Java, and Python. Let's take a look at the C++ implementation. We'll read in n the number of nodes, and then we'll read in our BFS and DFS orders. After that, we'll check if we have only one node. If we have only one node, there's no edges, so we output 0 and then end the program. Next, we need to check if the first child matches. If it doesn't, then we output -1, as this is not a valid ordering of nodes, and then we return 0. If we've made it past these checks, then we output the number of edges, which is 2 times n minus 3, and then we print out our BFS edges. Our BFS edges will just be between 1 and each other node. After that, we'll output our DFS edges. Our DFS edges need to skip the edge between node 1 and the first child because the BFS already covered it. After that, we'll print the DFS edges, which are just between each adjacent pair of nodes. That's all for the C++ implementation. Next, we'll take a look at the Java code. Let's take a look at the Java code for this problem. We have n, the number of nodes, and our BFS and DFS orders. We'll read in the orderings, and then we'll check if we have only one node. If we have only one node, there's no need for any edges, so we'll output 0 and we'll end the program. Otherwise, we need to check if the first child of both traversals match. If they don't, we output -1 as this is not a valid set of traversals. Otherwise, we output 2 times n minus 3 for the number of edges, and then we output the BFS edges. The BFS edges will be between 1 and each other node. After that, we'll output the DFS edges. The DFS edges need to skip the edge between node 1 and the first child because BFS already covered it. Aside from that, the DFS edges are just between each adjacent pair of nodes. That's all for the Java code. Next, let's take a look at the Python solution. Now let's take a look at the Python solution. We'll read in n, the number of nodes, and the BFS and DFS orders. After that, we'll check if we have only one node. If we have only one node, we have no need for any edges, so we'll output 0 and end the program. Next, we check if the first child of both traversals match. If they don't, we output -1, as this is not a valid set of traversals, and then we'll end the program. If we have a valid set of traversals, we output 2 times n minus 3 for the number of edges, and then we'll output the BFS edges. The BFS edges will be between node 1 and each other node. After that, we'll do the DFS edges. The DFS edges need to skip the edge between node 1 and the first child because BFS already covered it and we do not want any duplicates. Aside from that, the DFS edges are just between each adjacent pair of nodes. That's all 3 language implementations done. Thank you for watching this video.